name's Dr. Dave DeSimone. I work for Dr. Salehi in the civil engineering department here at the University of Memphis. It's an honor to be here today, and I appreciate you all asking me to take a few minutes to speak about what I've been up to and what Dr. Salehi has been up to during this tumultuous year, let's say. We've actually taken and I'm going to go into this in a moment, but we've taken the COVID-19 experience to be kind of an opportunity in disguise. Just a quick background on Dr. Salehi's research, because that'll lead into what I've been doing. She's done some great work in the field of environmental engineering, specifically looking at drinking water, and within that realm, looking at heavy metal concentrations and the parameters and the variables that influence heavy metal uptake into certain types of drinking water piping, some transport processes, and some kinetics, looking at, like I said, the heavy metal fate and transport within drinking water applications. She's also currently going into stormwater applications as well. So that has all been happening prior to me and prior to my work at the University of Memphis. So when I had the opportunity to work for Dr. Salehi toward the end of 2019 and through 2020, I had gone into the project with the thought of doing more lab work, looking at heavy metal absorption into polyethylene pipes that transport drinking water, and how the lead and other heavy metals will absorb into the polyethylene piping and then potentially be re-released back into the drinking water, so that looking specifically at the concentrations of the heavy metals within the drinking water, and ideally trying to mitigate any parameters that will lead to high concentrations of lead and other metals in the drinking water. So that was all in theory, but then obviously COVID hit, and credit to Dr. Salehi, she was able to take this this pandemic, this obviously tragic situation, and kind of find a silver lining, at least from not just from a research standpoint, but also from a public health and humanitarian standpoint, and look at this specifically at the University of Memphis, and potentially to use this as an outreach methodology to show, hey, we have an unprecedented event here of all these buildings being shut down, all these public buildings, obviously here at the university, but then also in other sectors as well. Capacity is very low. The water is very stagnant in these buildings, and that situation in and of itself will lead to heavy metals being leached from the piping into the drinking water. So we have to purge that drinking water from the piping and ensure that when occupants reoccupy these buildings and these buildings are reopened, we need some standardized protocols to ensure that there's clean water in these pipes in these buildings. Yeah, the thought could be, well, let's just run the water for a short period of time to ensure that we have some clean water in these pipes. But after digging in through the literature, there's very few, if any, standardized protocols to ensure that the water will be clean. And if we are flushing the water, how do we know? How do we know that the metals that have leached into the water while the water has been stagnant, how do we know that that stagnant water has been properly flushed? Those high concentrations of metals, whether it be lead or tin or zinc or copper, have truly been flushed. So Dr. Salehi, to her credit, and myself and a few other graduate students, we all kind of took it upon ourselves to work with facility services to say, hey, the buildings are shut down right now. Let's take some samples of the water, see how the concentration is increasing over time as these buildings continue to stagnate and the water in these buildings continue to stagnate. Let's continue to take some readings to see how the stagnation is affecting the heavy metal concentration. And then let's flush these buildings according to a standardized procedure, and let's see how that flushing really affects the heavy metal concentrations. Let's conduct some tests. Let's compare this to the as-built plans to see, okay, we flushed this volume of water in this sequence, and the as-built plans show that the plumbing is of this diameter and this material and this length. So there's this hydraulic volume contained within each building. Uh, does our flushing methodology truly get all that water out and get all new water in? Let's take these samples and let's analyze them by various spectrographic methodologies to ensure that the metal concentrations have now declined after flushing. But then let's monitor the buildings to see how quickly those metal concentrations increase back up to their stagnation levels. How often do we have to do this flushing? And after several rounds of questioning with facility services and speaking with their team of how they typically conduct flushing, maybe it be after a summer recess or during a holiday break, we saw that there's a very wide range of responses of how flushing is generally conducted on campus and in other institutions as well. And there's a wide range of results, and there's a wide range of opinions. This quick presentation today will go into some of the things that we saw over the stagnation period, and then during the flushing period. So this is a brief timeline, and Raymond was nice enough to record this. So some of these slides I'll go through relatively quickly, but seeing how it's recorded, feel free to pause and read these. This is just a timeline of what the capacity of these buildings was. You can see that back about a year ago is when we were taking our samples, and during the summer we were taking follow-up samples as well, and then during into the fall is when we were doing the analysis. So our goal here was to look at this sample collection in general. We wanted to see our first draw. First draw is when you immediately turn on the tap, what is coming out. That is considered first draw sampling. And then flushing would be about 30 seconds afterward, standard flushing. But we saw that in general, that wasn't enough. We had to conduct flushing all the way back from the fire hydrant, ensure fresh water is coming into the fire hydrant, then go into the basement, find the point of entry into the building, flush at the point of entry, and then continue to flush at each sequential fixture all the way down the plumbing. A common practice when flushing buildings is just to either flush all the toilets or flush arbitrarily throughout the building or flush all at once. We found, and prior research has shown, proper flushing requires sequential flushing from the point of entry in the building, one at a time, to target each cold water fixture, whether it be a sink or a drinking fountain, all the way through the building, going from the first floor all the way up to the fourth floor. And so that's how we conducted our flushing, our sampling and our flushing, I should say. So when we tested on site, we tested for total chlorine, pH, temperature, dissolved oxygen, total organic carbon, and all these we were using as indicators to see if there were any correlations between those parameters and our end goal, which is the heavy metal concentrations in the building, which specifically we were testing for iron, lead, copper, and zinc. So like I said, we had to follow the as-built plans, and so we were looking at the as-built plans to see where the plumbing goes through the building. Unfortunately, not every building on campus that we tested 10 buildings at University of Memphis, seven academic buildings, 3 athletic buildings. Not all of them had as-built plans. Some of the as-built plans were out of date. There had been many renovations in the building, whether it be minor or major renovations, and all that affects transport of water through the building and hydraulic volumes overall. So once we were able to procure the as-built plans to the best of our ability, and to from the as-built plans determine the potential plumbing material that was used, and also the hydraulic volumes based on the length and diameter of the piping, we're able to come up with an idea of the flushing times that would be necessary given specific volumetric flow rates at each fixture. We could determine an approximate flushing time at each fixture, again sequentially through the building, that we would need to flush. But again, before we could do the flushing, we had to conduct the sampling to determine the stagnation, and we have some photos of that in a moment. And you can see that flushing was definitely necessary. So this is just kind of a process diagram of how we flushed, starting at the fire hydrant, like I said, then at the point of entry, then at the each individual fixture, whether it be cold or hot. Again, those follow 2 different lines. We did not flush the hot water tank from a logistics standpoint. Flushing the hot water tank would have released a lot of particulate matter into the hot water lines. Draining, I'm sorry, I said flushing. We did not drain the hot water tank. We just flushed the hot water tank by calculating the hydraulic volume in the hot water tank and ensuring plenty of turnovers. And so this is our general procedure that we followed here. This is a very busy table here, but these were the parameters and characteristics of from the, whether it be from the as-built plans or from our site investigations. This for each of the buildings, A1 through A10. A1 through A7 are the academic buildings. A8 through A10 are the athletic buildings. You can see the different specifications and characteristics of each of the building, whether it be the type of piping, how old it is. We gathered all this information to in the hopes of being able to generate some correlations between potentially age of building and what concentrations of heavy metals were absorbed into the piping, type of metal and concentration, heavy metal concentrations that were absorbed into the plumbing. And so this is just a summary chart of much of the material that we were able to gather. You see some of the highlighted cells show some of the challenges that we ran into, and that first red cell shows where building as-built plans were not available. A9, this is the athletic dressing facility where the football team practices, and you can see the huge volume of water that's contained in the plumbing. And this could directly correlate, or directly translates, I should say, to the amount of time required to flush. So let's look at some of the statistics we were able to gather. So here are some summary statistics before flushing. This is at the point of entry. So for the samples that we took at the point of entry before flushing, draw your attention to the median values here. We had pH just below neutral at 6.8. Temperature was a little below room temperature at 20.5. Dissolved oxygen as a percentage, 27.5, which was relatively good. Total chlorine, somewhat low at 0.5 milligrams per liter, and total organic carbon at 5.1. After flushing, again, this would be after we already flushed the hydrant and then retaking a sample. You can see the pH increases slightly, the temperature, because it's now a little, it's flowed through the building potentially a little longer. It's little warmer, not significantly though. DO increased, which is good. That shows it's fresher water. Chlorine increased, shows the chlorine has not dissipated since being implemented at the water services distribution plant. And total organic carbon, again, increased, but potentially not significantly. Main points here: median pH increase and overall range narrowed. So minimum was initially 6.5 to 7.7. You can see the minimum increase and the maximum decrease. So we have a tighter distribution on the pH. Temperature increase could be attributed to seasonal differences. Again, we did the before flushing in May, and after flushing sampling we did in July. Dissolved oxygen and total chlorine increased significantly, which was great. It shows it's fresher water, and TOC increased slightly. So what were we actually doing when we were flushing? We want to ensure that chlorine, in order to be confident that we have fresh water in the building, we want to ensure that chlorine gets up to the same chlorine concentration that's at the fire hydrant or the point of entry in the building. So this is a approximate times that were required in order to get the chlorine concentration up from its initial values to the flush values, which would be indicative of what's coming out of the water treatment facility. So you want your chlorine concentration to be up around at least 1 milligram per liter. You can see for hot water flush, it took significantly longer to get that chlorine concentration to increase. That's due to a couple factors. One, the heat readily makes that chlorine dissipate, so you have to have more of a buildup. But also, there's much higher hydraulic volumes in the hot water lines than the cold water lines. So here's just some distribution depictions of what we had said previously. pH, you can see it tightened for before flushing and after flushing. Dissolved oxygen, you can see we had some zero inflated data before flushing, and then aside from the zero inflated, relatively normal distribution. These are broken down based on athletic and academic buildings. But the dissolved oxygen after flushing significantly increased for both academic and athletic buildings. Same was true for chlorine, which usually those two go hand in hand, chlorine and dissolved oxygen. Low chlorine concentrations before, much higher values in the distribution after. Just for the sake of time, I'm continuing. I want to get to the results here of what we were targeting specifically, which was metal concentrations. Again, we measured the pH, the chlorine, the dissolved oxygen, all those to ideally have some indicators going forward to know how those correlate with what we're truly interested in, which is the metal concentrations. So I bring you to the metal concentrations. So you can see here a few box plots for copper concentration, zinc concentration, and lead concentration. On the left of each plot is the before flushing. On the right of each plot is the after flushing. So you can see for all three, copper, zinc, and lead, the median value, which is indicated by this middle line here, the lowest value of the box is 25% quartile. The line between the orange and the gray is the 50%, and the top of the gray is the 75% quartile. The outliers, for sake of visibility, are not depicted on these box plots because the outliers were very, very extreme. You can see our ranges here in milligrams per liter for these heavy metals are on all of them less than 1 milligram per liter, but on our outliers, we had them, there were outliers up around 20 milligrams per liter. So if I had included all the outliers, you wouldn't even be able to see the majority of the data. So they're truncated, but they are noteworthy, and we'll get to those in a moment. So like I said, if you look at the median value between the orange and the gray, you can see for copper, zinc, and lead, as expected, The copper concentration decreases significantly. The zinc concentration, again, median values, decreases significantly. And the lead concentration, again, taking into account the scale of the much lower concentrations overall, median concentration of lead decreases significantly after flushing. So that's good news. Copper and lead have defined EPA limits. So you definitely want those to be low in drinking water. And so getting the median values down was very, very important. And so it showed that by having standardized flushing protocols, which I'll again speak to in a moment, that definitely decreased the overall metal concentration for these three. Speaking again about the outliers that were high before flushing, again, they're not depicted on the figures. Key to keep in mind, oftentimes when you have box and whisker plots, there's a loss of information because you can see a box plot or with the whiskers, let's say, before flushing. And if I were to have the outlier posted, again, it would be several orders of magnitude higher. If I had it for before flushing and after flushing, not all box and whisker plots actually show that that point that's an outlier before flushing is actually the exact same fixture and is still an outlier after flushing. And that's critical to keep in mind because it's not just showing that there are outliers present, it's showing that the outliers that are present are the same outliers that existed before and after flushing, meaning flushing didn't do anything for certain outliers. So if the copper, zinc, or lead concentration was extremely high before flushing, then the copper, zinc, or lead concentration would still most likely be extremely high after flushing. So although flushing is thought of, or building flushing or flushing the water through the piping is thought of as a tried and true practice, and generally speaking, like you can see the decreases in the median show, although flushing is thought of as a tried and true practice that alleviates heavy metal concentration in drinking water, and even the EPA recommends it, and it is well used and it should be used. It does not work for 100% of fixtures. So if a fixture is an outlier before flushing it, and has very high metal concentration, just flushing that fixture very well may not decrease that metal concentration. And oftentimes, we've seen in our discussions with some of the building staff, that's thought of as the end all be all to rectify any high concentration. So if there's one takeaway here, that's what I want to leave you with, is just running a faucet for an extended period of time, even if it's done during by the exact protocol, it very well may not alleviate the high concentrations that are seen even before flushing. So you'll notice on that slide I left out lead. I left out iron, and that's for one specific reason. The iron concentration, again, we're talking median values, and median values are depicted by the middle line here between the orange and the gray. It actually increased from before flushing to after flushing. So when doing from a statistical analysis standpoint, and again, we, as you can see on the slide, we ran the Wilcoxon sign rank tests. Copper decreased, zinc decreased, lead decreased, and we saw that in the previous slide. The iron concentration from a statistical standpoint actually remained constant, and that's taking into account the 75 percentile here that decreased, the median value that increased slightly, and the 25 percentile that increased slightly. So overall, when taking all these as a sign rank test, flushing had no effect on the iron. Looking visually speaking, though, on just the median concentration, you can see that it increased. So there's a conflicting thought here. If your goal is to decrease iron concentration because you have high iron from either the galvanized pipes or any other source, flushing may not do the trick. So again, Flushing, even by the EPA, has been promoted and is encouraged, and it still is. But what we had seen was it's not an end all be all for all fixtures and all metals. There, it definitely has to be taken under consideration. Uh, so overall observations, stagnation definitely was influenced by both duration and capacity. So low capacity buildings had a higher stagnation, which is not rocket science. Fewer people were in the buildings, so fewer people were using the fixtures, so therefore the water stagnated. That stagnation, specifically over a long period of time, uh, led to heavy metal absorption into the water. Flushing at hydrants was necessary to ensure fresh water entering the building. pH exhibited slight increase, and jury's still out on why that was, but we assume it was because of the higher iron. Um, Metals, except iron, exhibited significant concentration decrease. Water quality has returned to pre-flushing values. So that's the other thing to keep in mind. This was quite an undertaking to do for 10 buildings, again, doing it in a sequential, methodical manner from the point of entry through every single fixture, all the way from the point of entry, all the way to the exit of the building, or the highest floor of the building, I should say. Took a lot of time because we had to do it one at a time. We flushed each fixture individually, and even doing it in the most methodical manner, according to as-built plans, we returned to pre-flushing values on follow-up testing within about a week or 2 weeks, depending on building capacity. So it's something to keep in mind. So if the buildings are going to be reopened, we encourage, and again, this is more prevalent now as we're getting back into on-site instruction, and also other facilities are getting up to higher capacity. Just in Tennessee, just over the last couple of days, we're back at almost 100% capacity. The thought is conduct the flushing right before the building reopens, and otherwise the point is lost relatively quickly. So here's some of the photos that we've seen, the range of rainbow of samples that we've taken from buildings, whether it be on site and at the University of Memphis or other buildings within Shelby County, other schools within Shelby County. So obviously there's a range of clarity, which in the business we call turbidity, in essence. And this is a range of metals that we saw, everything from, like I said previously, lead, copper, and iron, to other metals that we even tested for, zinc being one, tin being another. And based on the building infrastructure and based on the age of the building, based on the capacity, we saw quite a range. But because of all this, we were able to, and we're in the process of publishing this, developed standardized flushing protocols based on capacity, based on as-built plans, hydraulic volumes, piping, meaning the metals, whether it be galvanized iron, copper piping, and based on the size of the building overall, which is what we contributed from a practical standpoint to, again, Dr. Salihi's theoretical research previously. So this was kind of a change of plans from what I was brought on originally, but given the situation with COVID-19, it was quite a troubleshooting experience, I guess, to make lemonade out of lemons, I guess, for lack of a better term. But with that, I'm happy to answer any questions, whether now or in the future. Feel free to email me there. Although my postdoc has officially ended from the university, I'm still working with Dr. Salihi on publishing this and a couple other projects that we've been working on. And I look to actually teach in the fall at the University of Memphis. So email address is still active, so anyone can email me at any time. Thank you very much.
Thank you, Dave. It's been great. I will follow up with you when we do any future sessions, and when there's been any updates to your research. Thank you so much.
Thanks a lot. Appreciate you having me.
Yep. Thank you. Bye.